Welcome back. Today in this video we are going to see how to prove proof obligations automatically and interactively. The automatic proof is a push button activity and a quick process most of the time. The automatic prover can be run with forces from 0 to 3. The higher, the better proof percentage at the cost of a longer computation time. Only forces 0 and 1 are reachable from the main window toolbar. Forces 2 and 3 can be triggered from the component menu. The automatic proof uses the interactive command PR with the corresponding force from 0 to 3. It is, however, possible to define its own automatic proof tactics when the user passes when an interactive proof has been successful. During interactive proof, you are automatically asked to save successful demonstrations in order to reuse them later for similar proof obligations. You can specify filters on the name or on the predicate to be more efficient by executing tactics only on selected proof obligations. The resulting user demonstration is then saved in the PMM file of the component stored in the user path theory, also reachable with the Edit PMM in the model editor window. This file will also contain the additional mathematical rule added to complete some proofs. This feature will be covered in a future video. To add a user path for a component, you need to open the component, to open the PMM file, and to add the user path here with 3 commands. When you save it, you obtain 3 commands that you are able to trigger. Just go back to your component, unprove it. So everything is unproved, and then execute the proof using the user path. And you can have here a look at all the statistics and how your proof obligations were demonstrated using your user path. Several tactics can be defined in a user path. They are named and they are ordered. When multiple tactics, the prover will execute the first tactic on the selected unproved proof obligation. Then it will execute, if any, the second tactic on the remaining unproved proof obligations, and so on. When the proof has been completed, double-clicking on the component name in the task pane will show up a window indicating which tactics have been used. The proof status of the model display in the model editor corresponds to the proof with the automatic prover in force 0. This view does not take into account the specific proof tactics you possibly developed. This view is supposed to provide a quick feedback. If you want to execute a given proof tactic, you need to switch to the Atelier B main window. Interactive proof is an activity that requires some experience with the automatic prover and a good knowledge of the model being proved. Some predicates are more easily proved automatically than others, so during interactive proof, the user is in charge of adding information or transforming the predicates in order to complete the process. 2 different users will probably develop different interactive demonstrations because of their own experience and habits. In the interactive prover, the most important area is the view representing the current goal to prove. Only the contextual hypotheses are displayed in this view in order to optimize the ergonomy and to ease the visibility. Most interactions with the goal and searches for hypotheses are performed through context menus in this view or by using textual commands. Double-clicking on an identifier will highlight all its instances. A right-click will show a context menu with several action possibles, and we'll be able to get all the hypotheses containing the symbol. The same results can be obtained by typing message of next, sh of A shows all the hypotheses, and sh of A is equal to B shows all equalities. So we are going to see how we can use interactive and automatic proof to demonstrate proof obligations. So we have a collection of models, we have a context machine, we have a specification, we have an implementation with remaining unproved proof obligations. So have a look first at the specification. So the remaining unproved proof obligations has nothing obvious. So let's start the interactive prover and go to the only unproved proof obligation. We do a deduction to get the predicate. We're looking for the definition of next. Next is defined as an equality. So we are replacing next with this definition by using use equality in goal. We obtain a new predicate. Now we're looking for SS. Such hypothesis again. SS belongs to T-state, so we could imagine starting a do-by-case proof using the command DC. And so we obtain 4 different subcases. The first one, SS is equal to E3, then E2, E1, and E0. So to simplify the predicate, we use simplify set command, SS, simplify to be true, MP to prove it. So we move to the second case. Again, SS, MP, proved. Third case, SS, MP, proved. And last case, SS, MP, it's proven, it's green. Now we save it, and we ask to create or update the user path, press OK, then next, and the user path is created for us. At the end, for the operation assertion lemma, for a proof obligation of form not of A, in for 0, we performed a deduction, use equality for next, so proof by case, and then the commands SS and MP in sequence. We finish it, we improve the component, we prove it again using user path, and everything is proven. If we double click on the name of the component, we can get the statistics about the proof, and we can see that the last one has proved the proof obligation. Now, have a look at the implementation. So we have remaining unproved proof obligations. The first one, initialization 1, is obviously wrong. False is not equal to true, so we probably made a mistake. So have a look at the specification. B1 should be equal to false, so we need to correct the implementation, replacing true with false. No, false, because in this case we are doing exactly the same thing, so true by false, we save it, and it's proven. Now have a look at adapt, so we have a if then else substitution, and we expect that SS belongs to the next of SS. Have a look at the definition of next. E0 is associated to E1, E1 associated to E2, E1 to E3, E2 to E3, and E3 to E1. So we do not have any element associated to itself. So the if then else sequence is correct. And so the only reason is that we made a mistake in the specification. SS should belong to next of the previous version of SS. So we correct with $0, we save, it's demonstrated, we update the status of the implementation, and the complete model is now proven. You now have a better knowledge of how to conduct a proof, and you are ready to gain some experience with automatic and interactive. This is all for today. See you soon, and remember, formal is fun.